I'm going to talk to you about experiments on the fluid mechanics of growing icicles, and in particular, this strange ripple pattern that appears on growing icicles. If you're a good Canadian, you've seen a billion icicles and you've noticed this beautiful ripple pattern. These experiments are being done just up the street from the Fields Institute. I wish I could show them to you, but sadly I cannot. I'll just show you pictures. Most of the work I'm going to show you is by my former graduate student, Anthony Suhan Chen, who is now at the Southern Alberta Institute of Technology. And the present experiments are being done by John Layden, who is, I think, even in the lab today. And we are just up the street. So what's an icicle? An icicle is a piece of ice, and you make ice by taking water at 0 degrees Celsius, and you remove a certain amount of heat from that water, a certain amount of latent heat, and it switches to ice at 0 degrees Celsius. So in order to grow ice in a dynamic way, it's basically a heat transport problem. You've got to remove the latent heat. And so when an icicle grows, what happens is the flowing water at very close to 0 degrees flows over existing ice, and somehow it loses its heat and adds to that existing ice. And so icicles are growing by a thin film of supercooled or cold water on their surface. And so the whole question is exactly how that surface impacts the flow of the water and how that impacts how the heat is removed, because that determines how the icicle grows. I'm not going to say too much more about it, but stalactites, that is the things that hang from the top of the cave, are formed by a sort of analogous process. In a stalactite, it's calcium carbonate that's dissolved in the water, and the chemistry of CO2 is such that when the CO2 comes out of solution, it changes the chemistry of the solution, and the calcium carbonate is deposited. The main difference between stalactites and so the dynamics of the CO2 is similar to the dynamics of the heat that has to be extracted to grow the surface. The main difference is it's a very tiny fraction of dissolved impurity that can be growing in the case of a stalactite. In the case of an icicle, it's the water itself which is being extracted. So the water is consumed as it runs down the icicle, at least a little bit, and the water is not consumed in the case of a stalactite. But the theories and the ultimate shape of the thing are quite similar in the two cases. So this is a kind of pattern formation that I like to say is ubiquitous in nature. We always like to say that. And so basically you have some kind of shaped surface and some water flows down it under gravity. And then something happens to change the shape of the surface: erosion, transport, deposition, dissolution. And in the case of icicles, it's growth. And that occurs relatively slowly. And so the surface evolves slowly compared to the rate at which the water flows. And there's a complex feedback between the flow and the shape. So how does it know what shape to be? Well, it depends on where the water flows. And how does the water flow? Well, it depends on the shape. But crucially, there's a separation of time scales. It takes very little time for the water to run down the shape, but a very long time for the shape to grow. For an icicle, that growth time is many hours, perhaps as many as 12 hours, 6 to 12 hours. For a stalactite, it can be hundreds of thousands of years, so it's very slow. But it only takes a few seconds for the water to run down the icicle. And so the feedback is very complex, and we don't a priori know what shape is going to emerge from it. There's actually 3 distinct ways in which icicles grow. There's the obvious one: the tip gets longer, and that's called mode 1 by these glaciologists who've studied this. In mode 1, there's a pendant drop hanging from the bottom of the icicle, and that supplies a kind of bulk amount of water. And as that drop cools, it forms ice on the ends of the icicle and makes it grow longer. And that's a fairly efficient heat transport there, so the tip grows relatively quickly. In mode 2, the shank or the sides of the icicle, the radial growth of the icicle, is slower, and that grows from a thin film of water, or as I'll show you, little drips of water that run down the outside. But they're thin, and so that turns out to be a slower mode of growth. So the main reason why an icicle is long and pointy is simply that the tip grows faster than the sides. And there's a third mode of growth, which is not obvious at all unless you stare at icicles for a long time, but that mode is called mode 3. And in fact, the tip of the icicle is usually kind of hollow. It's like a straw or something. And there's water, liquid water, trapped inside the tip area, which does not freeze because there's no temperature gradient to take the heat out. And that can actually remain liquid for quite a long distance up the icicle. And eventually it loses heat through the sides or through the point of support, and that freezes up that pipe, and that's called mode 3. I won't say anything further about mode 3 and mode 1. The ripple problem is all in how the shank of the icicle, the sides of the icicles grow. So how do you study icicles? Well, you build a machine, okay? So just up the street from Fields, there's a lab in the McLennan building, and it contains the world's only dedicated icicle growing machine. And this is what it looks like. It's a big refrigerated box connected to a computer. This is a 36 megapixel SLR camera, which takes pictures through this thing we call the camera tunnel. And inside here, there is a support, and all this electronics maintains temperatures and water flows and drips water very slowly into the box and forms an icicle inside. And the whole thing is refrigerated by a circulating bath. So this is what it looks like schematically. We push water in very slowly at the top, and it drips onto a little piece of wood, which is pointed. And as the water drips off there, it forms an icicle, and the water that drips off the tip is captured by a funnel and removed from the experiment. And we rotate the point of support very slowly. And the reason for that is there's at least several different reasons. One is that it's just kind of cool to make rotating icicles. A second reason is that we want to make the icicle as axisymmetric as possible. So we rotate in order to stir out all of the radial temperature gradients that would otherwise be there. Another reason is that the computer that's taking pictures of the icicles is kind of stupid, and the only thing it can do is capture the edge of something. And so by rotating the icicle, knowing the angle that it's rotated to, taking a picture and rotating again, we can reconstruct the three-dimensional shape of the icicle. So this is kind of an icicle 3D scanner. And also we move the tip of the nozzle slightly off axis from the dowel so that the water is kind of distributed in an axially symmetric sort of way around the outside. So here you see the icicle looks like it's tearing around really fast, but in fact, it's taking about 1 second for every 10 minutes of real time. And this is distilled water, and you see it grows a very symmetric looking sharp icicle, which has a nice simple shape. If I use tap water, and now I'm showing you a stroboscopic movie so that the icicle appears to be stationary, but in fact, it's the same icicle growing 8 different times from 8 different points of view of the same icicle growing. It's rotating, and I'm taking a picture every 8th of a rotation. Now you see that the icicle is not so smooth. In fact, this ripple pattern has appeared on the sides of the icicle. Most natural icicles do have ripple patterns. So what's the difference between tap water and distilled water? That turns out to be the crucial question. Natural icicles are often ripply, and of course, in that case, the water is not distilled. It's just natural water running off of your roof. And here's some pictures of these two are taken on my house in Toronto, and this one is taken by a guy in Utah, and I got permission to use it in publications because it's so pretty. What we see is a regular pattern of ripples develops during the growth. What do we know about the ripples? Well, from observation, we know that they're almost always about exactly 1 centimeter in wavelength. If you count the bumps in this picture and the ruler, you'll see that they're pretty much 1 centimeter between the bumps. Ripples are not observed on distilled water icicles. They're smooth. So there's something to do with the water purity is important. Unfortunately, a large body of literature already exists on theory of the icicle ripple instability, and it assumes that the whole thing is due to pure water. And it assumes basically that there's a thin film covering the entire surface, and it's the modulation of heat transport through that thin film, which gives rise to the modulation of the growth rate. And I'll come back to how the theory works later. But this theory by Kazuto Ueno, and if there's a few other people involved, they basically do not have impurities in their theory at all. So it can't be the whole story. The icicle ripples have a strange and long history. They were first discussed by this famous Japanese physicist named Torihiko Terada in a paper way back in 1933. And there is the first scientific paper. This is a kind of popular article called Stripe Patterns in Nature. And it's kind of the founding article for pattern formation in Japan. Unfortunately, it's never been translated into English. And so Terada is an almost unknown figure in pattern formation in the West, but he's a kind of hero of Japanese science. The first actual publication, this is pretty much the whole publication in Japanese, And it just says, I've seen an icicle with ripples, and the ripples have a wavelength of about 8 millimeters. And this is the Japanese word for icicle, which is surara. And there's some more experimental work, but until we actually made controlled experiments, there were very few experiments on the growth of icicles. Okay, so here's the crucial experiment. We start with, on the left, distilled water, in the middle, scientific tap water, that is distilled water with a tiny amount of sodium chloride added, just enough to give it the concentration of tap water. And on the right, somewhat higher concentration of sodium chloride, just salt. Now this is, by the way, still a very long way from seawater. Seawater has many grams, 35 grams per kilogram of salt, and this is only milligrams or micromilligrams of salt. So the level of impurity required is very low. And what you see is that these two icicles have about the same shape, but this one is decorated with the ripple pattern and this one is not. And if you add more salt, it develops a very strong ripple pattern, but it also develops a much more bulbous shape. So now we can look at the topography versus the time. For a distilled water icicle, we see the topography is fairly smooth. This is just the trend removed shape of the right-hand edge of the icicle. And when the ripples are present, you see them appear and they grow to about 1 millimeter in size. And as I was saying, and I'll show you the data, they're separated by about 1 centimeter, but it's kind of patchy. There's a little patch here, a little patch here. This is time of growth. This is the tip growing downward, and these are the ripples growing. For the larger concentration of salt, the ripples grow to a kind of maximum saturation, and then they actually become kind of dynamic or kind of complex. So this is 8 different rotational views of this blobby looking icicle. And here you see that from different angles of view, the ripples are different. And so on some sides, there's almost no ripples. From other sides, there are ripples that kind of collide with each other and are complicated. So now we can just empirically look at how the ripple amplitude grows with time. If you start with just distilled water and there's a kind of noise floor where the ripples, whatever signal just stays constant and it doesn't grow. As you add more concentration of salt, the ripples grow and grow faster and faster the more salt you put in, and they grow to a larger amplitude, saturation amplitude. All the icicles I'm showing you have been in contact with air, so they also have dissolved air, and then in addition to dissolved impurities. If you make a distilled water icicle with just dissolved air, it turns out not to form ripples. So the air doesn't seem to have the same effect as the dissolved impurities do. If you go back to Ueno's theory, he blames the ripples partly on the surface tension of the water-air interface. And so we mess with the surface tension by adding surfactant, which can drop the surface tension by almost 50%. It's called Triton X, but it does not actually change the conductivity of the water very much. So it's like a non-ionic impurity. And when you add distilled water with reduced surface tension, you get no ripples. So that's what the yellow symbol. Now you can start adding both salt and surface tension modifying soap. And as far as we can tell, the soap makes no difference at all. The ripples are the same with or without the soap. We haven't done a million experiments with this because it's starting to get very complicated. But basically, it looks like the surface tension doesn't matter at all. Now you go crazy, you try everything. You try all different flow rates and temperatures and all different concentrations, and you collect a lot of data. And this takes a long time because it takes an all day to grow an icicle. So every run you do takes a whole day. So here's a summary of all this data. You can ask, how fast does the amplitude grow in time as a function of the salinity? Well, this is the growth rate of the amplitude versus the salinity. And what you see over a very wide range of salinities, orders of magnitude, is that the growth rate is only about linear on this plot. So it's only logarithmic with the concentration. It only grows like log C approximately. These icicles up here are very blobby, so it's kind of hard to say. But down here, basically the trend is linear. What about the wavelength? Well, it turns out that over a very wide range of impurity concentration, the wavelength is still 1 centimeter pretty much. It's extremely constant. All the different colors correspond to different growth rates and to different temperatures and flow rates. So the wavelength is independent of the concentration and everything else. So we've never made an icicle where the wavelength was consistently different than 1 centimeter. So now you can actually look at how the ripples move if you focus your eye on the left-hand side for a low salinity icicle and focus on a bump. You can tell me whether you think it's going up or down. I'll give it away. If you look closely, you'll see the ripples actually climb the icicle slowly. Now the actual ice doesn't move. What happens is the new ripple grows slightly faster on the top edge than it does on the bottom edge. And so the new ice is a little bit farther up than the old ice. And the ripple therefore climbs the icicle very slowly. If you look at a high concentration icicle, you see the opposite effect. If you focus your eye on the ripple, you see it clearly moving downward. And so the ripples descend for large concentration and they ascend for high concentration. And in between they cross over. So for low concentration of salinity, ripple is always traveling upward. These are the space-time pictures showing the ripple peaks traveling upward. And on the right, the dynamics is more complicated, but on average, the ripples go downward. Now, this is kind of funny because there were 2 theories and 2 theorists and 2 different possible signs of the eigenvalue in their theory, which gives you the traveling rate of the ripples. One said they would move up and the other said they would move down. So they're actually both right in some different regimes. Ueno said that they should travel upward. There's some more phenomena that we've uncovered. If you section an icicle and look at the interior, you find that it's not clear ice. There are inclusions or foggy areas inside the ice. And if you look closely, you can see that the foggy areas trace the peaks of the ripples, and they move upward. In the case when the ripples move upward, you can see these kind of chevron patterns inside the ice. And these the clear areas correspond to the dark areas correspond to clear ice, and the other ones will correspond to foggy ice or ice with inclusions. And the upward traveling is reflected in this pattern inside the ice. This is the first time this has been seen on an experimental icicle. It was actually noticed on a naturally ripply icicle by some glaciologists from Japan. So now we can do experiments where we add dye to the water. And so instead of using pure water with salt, we use pure water with a tiny amount of fluorescent impurity. And the fluorescent impurity acts like the impurity necessary to produce the ripple. So now we have ripply icicles, and we can trace where the water is going by looking at where the stuff is glowing. Dye in liquid water glows green, where dye in solid ice is a kind of orange color. And you can pull apart those 2 things. So here we see an icicle growing, and you see the tip going downward, and the tip is completely covered with dyed water, but the sides are not. You see the water is actually, the running water is actually confined to, let me just do this again here. Running water is actually confined to little rivers that run down the sides of the icicle. So this box is following the tip here, and this box is just showing the sort of shank of the icicle. And so you see as it gets larger, the ripples grow, but the water is kind of patchy on the surface. So this shows that the surface flow is fairly complex and doesn't uniformly cover the whole icicle. And so this shows up nicely in false color. If you false color it, you can see that the water actually hangs around on the ripples in that way. Now, if I look at a dyed sectioned icicle, you see that the dye actually ends up preferentially where the inclusions were in the previous picture. And so we believe that those are actually inclusions of impure water separated by pure water. So the dye ends up on the peaks of the ripples. Okay, now how much time do I have left? I'll talk a little bit about the theory, but I emphasize that the theory is in a state where it really doesn't work. Why would adding an impurity have anything to do with growing or not growing ripples? Well, it's because if you add a small level of impurity, sorry?
About 20 minutes.
Oh,
yeah, about
excellent.
20,
Okay.
25 minutes, yeah.
Oh, okay, okay. So let me explain how the theory works. The assumption is, and this is a very strong assumption, which I've already shown you is not true. The assumption is that there's a thin film of supercooled water completely covering the surface of the ice and flowing downward. And the theory is, of course, axisymmetric. We can't do anything but axisymmetric. And there's a base state where the water is flowing in a thin parabolic shear flow on the surface. And now you can ask yourself, how big is the temperature difference across this thin layer? And it turns out that almost all of the temperature drop happens outside in the air. So maybe I'm growing my icicles at 12 degrees, minus 12. The ice water interface is very close to 0 degrees. And so where is the temperature drop? It turns out almost all of it is in the mixed air outside, and only a very tiny millikelvin or tens of millikelvin temperature drop occurs across the water. Now, if I add a tiny amount of impurity to the water, the freezing point is depressed because a freezing point of dirty water is lower than the freezing point of clean water. And it turns out, if you look at the slope of the cooling line, that level of freezing point depression is also in the sort of tens of millikelvins. So this is a clue that the reason it's so sensitive to the tiny amount of impurity has to do with the fact that the cooling that's actually driving it is this very small supercooling, and that's easily achieved also by tiny amounts of impurities. So compositional freezing point depression is probably crucial to the theory. Another sort of complexity is that there's a free surface of flowing water up in contact with cold air, which is actually turbulently flowing. And so when you go to calculate the boundary conditions and ask how fast does the water cool, it turns out that evaporation, condensation, radiation, and advection diffusion are all present in the air. And so they all contribute about equally to the rate at which the heat is transported away from the surface of the water. So this is kind of like the heat transport problem from hell. Even the radiation from the icicle to the surroundings is a significant loss of heat. And the water is in contact with dry air, so a little bit of it evaporates, and that carries away heat too. So at the water-air interface, there's a complicated boundary condition involving all forms of heat transport. At the water-ice interface, we have a thing called the Stefan condition, which just links the fact that as the ice grows, it releases latent heat, and that heat has to be transported away from the surface to maintain that rate of growth. So we have to, just for the thermal part of the problem, we have to account for all forms of heat transport in the air and for the Stefan condition on the ice water surface. And so now what is the effect of impurities? If you look at how the temperature goes down as a function of the increased concentration of impurities, for very small levels of impurities, it's approximately linear. So there's this thing called the liquidus line is a very linear for very small impurities. So the freezing point at the surface is equal to the equilibrium freezing point minus a positive m times the concentration there. And as the ice grows, it excludes the salt, and salt builds up near the surface, and that causes the freezing point depression to increase. And so the proposed boundary condition on the temperature involves this special term. And this is the only place in my version of the theory where the concentration and the temperature talk to each other. The only physics is freezing point depression. So now, as I was mentioning before, the freezing point depression associated with the concentration in the water and the temperature gradient in the water, which is they're both very small, but the ratio of them is order 1. So that means even though the water is only supercooled by 50 millikelvin, the freezing point depression is only 50 millikelvin too. So it's actually an order 1 effect. Okay, so now how the theory works is you start with an axisymmetric theory. You just forget about the shape of the icicle completely, pretend that it's a plane with a parabolic shear flow on it, and then write down the advection diffusion equations for water flowing down a corrugated surface. And you assume that the water flow responds instantly to the topography, because the topography is changing very slowly. And that gives you 2 advection diffusion equations, steady state advection diffusion equations, one for the temperature and one for the concentration. And the whole problem turns out to depend on the Reynolds number, the Weber number, which contains the surface tension. So that tells you how the free surface behaves. But those things are actually not independent. They depend on this funny combination of the wave number of the ripples and the ratio of the Reynolds and Weber numbers. And because there's 2 advecting diffusing things, one is the heat, that turns out to have a Peclet number around 5 or order 1-ish, which means that basically the heat is advected quite quickly. And the Peclet number of the concentration is very large, which tells you that basically the concentration diffuses very slowly compared to how fast it's advected. And then there's one more number called the Stefan number, which gives you something about whether the temperature gradients are in equilibrium with the rate of growth, and it's very large. So that tells you this is slow growth by some standards. Okay, so the name of the game is to solve for the advection, sinusoidal perturbation of the surface, and how does that modulate the advection diffusion of the heat and salt through the thing, and how does that feed back to the growth rate through the Stefan condition. It turns out there's an awful lot of boundary conditions. There are 4 fluid dynamical boundary conditions. There's 2 on the concentration, 1 linked to the growth rate. There's the Stefan condition. There's a free temperature condition, which is complicated. And there's another one that links, the key crucial one links the impurity concentration and the surface of the ice temperature. That's the only place where the boundary conditions where the temperature and concentration talk together. The only 2 that really are crucial are the ice-water interface boundary condition, which I showed you a minute ago, where the temperature and concentration are connected. And then there's this complicated Robin condition at the surface, where the surface boundary condition involves both the temperature and the gradient of the temperature, and a linear combination of the 2. And this lambda turns out to depend on advection and radiation and transport. If you go back to Ueno's theory, basically Ueno has exactly the same equations, but with no concentration. He has no concentration of impurities. But crucially, it turns out, and it took me years to figure this out, he makes an extra assumption. He makes an unphysical assumption. He assumes that both the temperature and its gradient are separately constrained at the free surface, not a linear combination of the 2. And then he leaves the surface temperature unconstrained. So you need 2 boundary conditions, a second order equation. So he takes these 2 as his temperature boundary conditions. Whereas I have these 2, okay? And they're crucially different because this one constrains the temperature at the surface and he leaves it unconstrained, which is very strange because the one thing you know for sure is pure water freezes at Tm. But unfortunately, his theory doesn't enforce that thermodynamic condition. It just leaves that unconstrained. And so what happens, of course, is that he gets he puts this all in and solves for an eigenvalue. And he gets an eigenvalue with a maximum growth rate at the right wavelength and all of that. But there's something wrong because basically the boundary conditions are unphysical. If I use the correct physical boundary condition, include the concentration, then I get fields that look like this. This is the stream function, the temperature, and the concentration. Perturbation. This is the ice-water interface, which is, I've exaggerated it like this. And this is the temperature. You see what happens is near the peaks of the ripples, the temperature is higher, and it's lower here because this is growing faster and it's shooting out more heat. But there's no structure in here because the Peclet number is so low that it conducts really fast. And then this is the concentration. So here you see the salt is being excluded faster and slower at the peaks. So you put all this together and you get a consistency condition, which gives you an eigenvalue, which a complex eigenvalue, the real part of which should be positive if the ripples are growing and negative if they're not. And so here's the growth rate as a function of the wave number. And this dotted line corresponds, what we would like to see, I guess, is a peak is a bump with a peak near 1 centimeter where the instability appears to grow. But what we see is completely nothing like that. We see, in fact, that the eigenvalue diverges at large K. So this is a kind of ultraviolet catastrophe. There's no short wavelength cutoff. Infinitely small ripples grow infinitely fast. And it isn't even very dependent on the concentration. If I change the concentration to 0, this thing should be stable because that's what we see. But it isn't stable. It isn't even all that different if I add concentration. So this is a complete failure of the theory. It's not even sensitive to the thing that it's supposed to be sensitive to, and it diverges all the time. This is a kind of unstable situation. If I go to look at the Weber number, this is changing the Weber number, just changes the surface tension. And as I showed you in the experiment, that doesn't seem to have any effect at all. But it actually, if you change the Weber number over a large range, you sort of get the hints of a peak, but it still diverges at large wave number. And this variation is not as we expect. In fact, none of the peaks occur particularly close to 1 centimeter either. So I could summarize the situation by saying, at present, in spite of considerable effort, the linear stability theory of impure icicle ripples fails completely to account for any of the observed phenomena. So that's my conclusion. Ueno's linear stability theory doesn't include anything about impurities, so it's got to be wrong from the get-go. But upon close inspection, it also contains unphysical temperature boundary conditions. If you relax those and make them the same physical boundary conditions as mine, only with concentration equals 0, he gets the same divergence as I do. He also is forced to assume an axisymmetric, stable parabolic shear flow in the unperturbed state. And as I showed you, that's not a particularly good model of how the water actually flows down the icicle. In fact, it's little rivers are flowing down the icicle, and it doesn't cover the whole surface. The flow doesn't cover the whole surface anyway. It might on average, but it certainly doesn't instantaneously. And of course, the Ueno's theory completely ignores the interior of the icicles, and it doesn't contain anything about where the dye might lie inside the ice once it's frozen. And as I showed you, we observe all kinds of structure inside the ice, which isn't in the theory at all. So that's the unfortunate situation. If you generalize Ueno's theory using all the right physics, it simply does not work. It diverges and is very unphysical. So we tried some other experiments. If you start with a cylinder made of ice and just dribble fluorescent dyed water over the surface, you might think you would grow ripples. That makes sense, right? So here's a pure ice cylinder where we dribble water with fluorescein in it over it. And you see the cylinder is growing, which means the ice is forming, but you don't see any ripples forming. Do you? So this is a strange thing. This shows clearly that it depends on the interior structure of the ice, not just on the shape of the water flow and where the impurities go on the growing ice. No ripples form in this case. The impure ice grows on the cylinder gets thicker, but no ripples form. In fact, it grows by a factor of 2 or so. Here's a cylinder made of pure ice with a few places where we deliberately put in some dye to make some dyed inclusions there. Now, if you watch it grow, the same experiment, you see maybe a few ripples grow here, but I failed to nucleate ripples over the whole surface. So this is a sort of ambiguous result. Impure ice on this grows and the cylinder gets thicker, but no large-scale pattern of ripples grows. So it's not enough just to start with a little bit of impure ice on the surface to trigger the ripples. And this one is the funniest one. If we start with like a stub, like a bit of pure ice, which just ends and grow an icicle on that, what you find is that in the upper part, the dyed water happily flows over the ice without forming any ripples at all. But when it drips off the end, it forms a nice ripply looking icicle, just as it did before. So this is a kind of hybrid thing where the top part is refusing to grow ripples and the bottom part is growing ripples as it did before, and they're fused together right at the join here. If you look very closely, you see a single ripple starts to grow right above the join right there. There's a ripple growing. And the ripples are also climbing the icicle slowly. So impure ice grows, ripples forms, but basically it doesn't form ripples on the pure part. So these experiments seem to suggest that the ripples require not only the flow and so on, but they also have to have the right internal structure of the ice in order to grow. Okay, so let me conclude a bit. What are the burning questions? You like that? The burning questions are, why are there 1 centimeter ripples? We still don't really have a mechanism. We thought we did, but we don't really. Why do we need impurities at all to get the ripples? It isn't obvious why impurities have anything to do with it. I thought I had an intuition based on the freezing point depression, but that's just not true. So far as we know, that's the only physics that's involved, but we still don't know why. And why did all these phenomena happen? Like, why do the ripples go up or down depending on the amount of impurities? And what determines the pattern of trapped impurities inside the ice after the ice has formed? We don't know the answer to any of these questions. Theory completely fails to answer any of these questions. I've made a lot of movies and pictures of the icicle, so I'm enjoying myself, but I still don't know why any of this happens. Here are the gentlemen who are responsible for the experiment, and thank you very much for your attention.